Hello everyone. Today I'll be discussing on how computational tools are used in predicting thermodynamic behaviors through equations of state, or EOS for short, in the field of process engineering. We'll explore what equations of state are, why they matter, the computational tools available, their challenges, and how the future of this field is evolving with AI, high performance computing, and molecular simulations. By the end, you would have a clear understanding of both the theory and practical applications. An equation of state is a mathematical model that links pressure, temperature, and volume for a given substance. In process engineering, equations of state help us to predict how fluids behave under different conditions, whether in gas pipelines, chemical reactors, or distillation columns. Common equations of state include the ideal gas law, Van der Waals equation, the Penn-Robinsons, and the Solf-Redlich-Kwong. While the ideal gas laws works well at low pressures, real-world processes often require more sophisticated equations of state to account for molecular interactions and phase behavior. Equations of state are the backbone of thermodynamic modeling in process engineering. They are essential for phase equilibrium calculations, that is, predicting when substances will condense, vaporize, or form multiple phases. Thermodynamic property estimation. They are used in determining properties like enthalpy, entropy, and fugacity. Design of separation processes, such as distillation, absorption, and extraction. They are also used to simulate reactors and pipelines, thereby ensuring correct operating conditions. They are also used in safety analysis. They are used in predicting pressure buildup, vapor-liquid equilibria, and preventing accidents. Without equations of state, we would rather rely on expensive and time-consuming experiments for safety analysis. We are now looking at the computational tools which are used for EOS predictions. Manual equations of state calculations could be tedious, especially for complex mixtures. That's where these computational tools come in. We have the process simulators like Aspen Plus, Aspen Hysys, and Aviva Pro 2, which are powerful for large-scale industrial process modeling. We also have ChemCAD, which is often used for chemical process simulation and optimization. There is also the mathematical software packages, which include MATLAB and the Python libraries. These are great for custom equation of state development and research, mostly including mathematical calculations such as integration, differentiations, and what have you. There is also the specialized thermodynamic software, example DWSIM, which is an open source tool ideal for education and research. These tools speed up calculations, reduce human error, and allow for scenario testing before actual plant operations. Despite their usefulness, equations of states and computational tools have the following limitations. There is limited accuracy for polar or associating compounds. Compounds like alcohols, acids, and hydrogen bonding substances often deviate from the predictions which are made by these equations of state. There is lack of experimental data. Equations of state parameters depend on lab measurements, and for new or rare chemicals, these data might be unavailable. There is also computational cost. High precision simulations can require powerful hardware, and they could also be time consuming. Parameterization and binary interaction parameters. Finding accurate values for these is often a challenge. Engineers must be aware of these limitations and use sensitivity analysis to ensure reliability. Also, These equations of state and computational tools are integrated with other disciplines. Equations of state predictions don't exist in isolation. They integrate with disciplines like heat transfer, reaction kinetics, safety engineering, and environmental modeling. For example, in designing a liquefied natural gas plant, equations of state is combined with cryogenic heat exchanger modeling, compressor design, and hazard analysis. This interdisciplinary nature of EOS makes it a cornerstone of process design and optimization. The future of equations of state predictions using computational tools is indeed exciting. First, there is AI and machine learning for automating parameter estimation and improving accuracy. There is also cloud computing and high performance computing, enabling faster and large scale simulations. There is also molecular simulations using methods like molecular dynamics and grand canonical Monte Carlo for property prediction from first principles. Digital twins, creating real-time virtual models of plants for continuous optimization. There is also open source development, making advanced equation of state tools more accessible to students and researchers. These trends will make equations of state predictions faster, more accurate, and more integrated into plant operations. In summary, equations of state form the bridge between thermodynamic property and industrial application. Computational tools make equations of state predictions faster, more reliable, and applicable to complex real-world processes. While challenges remain, innovations in AI, cloud computing, and molecular simulation promise a future where equations of state predictions are both highly accurate and universally accessible. Thank you very much.